This is the second part of the videos on urinary system of human beings. This will be dealing with the Bowman's capsule and juxta glomerular apparatus. As we discussed in the first part of the urinary system, the nephron is the basic functional as well as structural unit of kidneys. The nephron is a fine long tubule, one end of which is opening into the collecting tubule and the other end is blunt. The blunt end is expanded into a cup-like structure, expanded and folded into a cup-like structure called Bowman's capsule. The Bowman's capsule, the structure of which is very suitable to its function. This is where the filtration happens in the kidney. The afferent arterioles enter into the Bowman's capsule and branches and forms the glomerulus. Then this glomerulus reunite at or near the entry of the afferent arteriole and forms the efferent arteriole. So this Bowman's capsule as well as the glomerulus together are called Malpighian body. Then this is where the filtration from the blood happens. The structure is very suitable for this purpose and we will see the structure of the Bowman's capsule. The Bowman's capsule has two layers of cells, an outer parietal layer of cells and an inner visceral layer of cells. The outer parietal layer of cells is a single layer of squamous epithelial cells. This has no role in filtration process at all, but it helps to make a capsule or space for the collection of the filtrate from the glomerulus. The visceral layer, this is also epithelial cells but modified having feet. They all have feet and their structure and their arrangement is suitable to aid in the filtration process. So this visceral layer or the podocytes rest on the basement membrane. The basement membrane, then after that you can see the endothelial cells. So this is a filtration barrier. The whole blood is not filtered into the or not moving into the capsular space. So the barriers, different barriers are there which control the filtration, what is filtered and how much is filtered. So first thing in the filtration barrier is the endothelial cells of the glomerulus. So the wall is composed of a single layer of endothelial cells. So the endothelial cells are not closely placed. There are gaps between the endothelial cells. So these gaps are called fenestrated. So this endothelial lining is fenestrated. So the width of this cavity, though the gap is around 70 nanometers, 70 to 80 nanometers. So only substances or solutes which are less than in size, that is less than 70 nanometers in size, can pass through it. So this will prevent the blood cells passing through the membrane. And then comes these endothelial cells are resting on the basement membrane. It's not a single unit. The basement membrane consists of three layers made up of the protein fibers. So the first layer, so it's a external layer, then the central layer and an internal layer. So these three layers are made up of protein. There are around 144 types of proteins present in this basement membrane. Among these 144 proteins, collagen type 4 forms around 50% of the proteins present in the basement membrane. And also out of the collagen 4, the subtypes alpha 3, alpha 4 and alpha 5 are present in the basement membrane. This is quite different from other type of basement membrane seen in human body. In the other type of basement membrane, you can see alpha 1 and alpha 2. And this basement membrane contains a lot of fibers. The fibers, these also got gaps. Around 10 nanometer wide gaps are present. Then above this basement membrane, you can see the podocytes. So these podocytes are also modified epithelial cells and they also help or control the filtration process. So these podocytes, they have feet-like processes. These feet interdigitate, forming filtration slits. So these are gaps through which filtration happens. So these filtration slits are also controlled or guarded by slit diaphragm. So they are extending between the feet. And these diaphragm has got minute pores through which filtration can happen. In addition to this filtration process and filtration slit, the glycoproteins are found around the feet. So they are natively charged glycoprotein. First we thought these natively charged glycoproteins control the movement of negatively charged proteins like albumin. But studies on genetically modified mice has ruled out this. So mice which have podocytes with less amount of negatively charged were studied, and it was found that even though there is less negative charge around the podocytes, the movement of albumin through this slit is very low. So the less albuminuria is formed. So that ruled out the principle that these negatively charged proteins repel the negatively charged proteins and controls the movement of filtration. This is another process near to the Bowman's capsule, juxta glomerular apparatus. So this is a modified part of the distal convoluted tubule. So it is very near to the entry of the afferent arteriole into the Bowman's capsule. That is why its name, juxta, very close to the glomerulus. So that is juxta glomerular apparatus. And the distal convoluted tubule comes in contact with the afferent arteriole, and that part is modified and forms the juxta glomerular apparatus. And this has got three types of cells. The first type of cell is the macular densa cells. These are sort of sensors. They are volume sensors. This is quite different from the other type of sensors present in the body, the chemical sensors. They are the sensors, majority of those sensors are strain or stretch sensors. This is volume sensor. This is a particular or unique type of chemical sensor found in the body. And their location is very unique because at this part of the tubule, the salt concentration of the salt is, the fluctuation is very high. So, depending upon the concentration of the salt here, the glomerular filtration or the kidney blood flow will be controlled. And this, the controlled by the macula densa is affected by the Na plus K plus 2Cl minus transporters. These transporters, they have a very high affinity to sodium. As a result, wide range of sodium concentration will not affect the response of this transporter or the function of the transporter. At the same time, their affinity to chloride ions are quite low. So very slight change in the chloride ions will, concentration of the chloride ions will affect its function and control the macular densa mediated response. So sodium affinity is high. So the wide fluctuation in sodium concentration will not affect the macular densa dependent control, whereas chloride affinity to chloride ions of this transporter is very low. So even a small change in the chloride ion concentration will affect the macular densa mediated control of kidney function. So this extraglomerular apparatus controlled one nephron. And the second type of cell is juxtaglomerular cells. These juxtaglomerular cells, they secrete renin. So this is quite different from the digestive enzyme renin, RENNIN. This is an angiotensin, it's a proteinase enzyme. This controls the excretion process. So it secretes, these juxtaglomerular cells secretes renin. The renin secretion is affected by the sodium chloride concentration. When the sodium chloride concentration is high, renin secretion will be decreased. When the sodium chloride concentration is low, renin secretion will be increased. So by controlling the secretion of the renin, the urine output or the filtration in the or the movement of blood through the glomerulus will be affected. Then the third type of cell, it is called extra-glomerular mesangial cells. These are also known as Purkinje cells. Their function is not well understood, but we suspect that as they are light staining pericytes. So pericytes are cells that wrap around the endothelial cells. So in the very minute capillaries or venules, they are covered by these pericytes. So they are sort of muscle cells. So they are present throughout the body. So in the juxta-glomerular apparatus also the pericytes are present. They control renin release and renal vascular tone are coordinated parts of the regulatory process of this. So the renin release that will control, or the signal from the macula densa control the vascular tone. These two are controlled processes which control the urine output. So this is through a renin, angiotensin, aldosterone system. So these three factors together constitute a system that will control the blood flow through the glomerulus. Or this is also called renin, angiotensinogen, aldosterone axis. So this regulates blood flow to the kidneys and the systemic circulation. And also it affects the systemic blood pressure, this system, renin, angiotensinogen, aldosterone system. Then arterial and venous vessels to the nephrons. As we discussed in the first part of the urinary system, the arteries from the abdominal artery supplies the kidneys, and the blood is drained into the inferior vena cava. So the arteries enter into the kidney sinus. They are divided into multiple branches, and finally they reach the cortical region, cortical radiate arteries. From the cortical radiate artery, if you see this next figure, so this cortical radiate arteries, the branches into the cortical region. This cortical radiate arteries, they give further branches. They form the afferent arteriole. So the afferent arteriole enter into the glomerulus. Then they unite together and forms the afferent arteriole. The width of the afferent arteriole is nearly double of afferent arteriole. But the lumen of these both arteries are almost same. The afferent arteriole wall is thicker with the more muscular layers. That causes its thickness double, make its thickness double of afferent arteriole. The afferent arteriole, after coming out of the Bowman's capsule, they branches off and give a branch which goes down and around in the tubule. It goes in parallel to the loop of Henle also, very close to the loop of Henle. So it's an extensive branch of capillaries. So that is known as vasa recta. So this controls, or this decides to a great extent the amount of reabsorption from the tubular fluid. So this vasa recta also forms part of the counter current mechanism, which will be discussed in a further session. Then from this vasa recta, the arterioles, the blood is taken into the venules, the radiate venules. From the radiate venules, it goes into the interlobular veins, from the interlobular veins to the lobar veins, from the lobar veins into the renal veins, and the renal veins drains or opens into the inferior vena cava. So this structure gives the flow of things. So by this, the second part is over. Thank you.